All right, APC, today's an exciting day. We're going to go around to the lab benches, do some magnetostatic stations. Oh, wait, choking. No lab benches involved. Okay, so here's some of the things that I would show you, except they're all in my classroom. So what I make you do is to go around the classroom and explore magnetism a little bit. So I have this styrofoam globe, and I make you take a compass and bring it close to the globe. And when you take that compass and you bring it close to the globe, you see that the north end of the compass points up to what we call the geographical north. And then as you begin to put the compass over here, you'll see that the needle begins to tilt. Doop. And then put it here, and our needle will become pointed inward a little bit. And so we can make that picture all around Earth. What a compass does is it has a magnetic north and south. So north is usually the red end of a compass. That's how it's represented. So what's going on? Well, this is what we call the North Pole, right? This is where Santa is. Santa. And at the North Pole is actually the magnetic south. And down here is the magnetic north. Now, that seems weird, right? Like, what? So at the geographical North Pole is the magnetic South Pole of our Earth. And so the magnetic field lines actually come out of the north end and travel around the globe and into the south. And so the compass that you are like probing around Earth with is going to point along those magnetic field lines with its north pointed in the direction of these lines here. Okay? Nice. So those are some examples of the magnetic field lines. Now, even though magnetism, it starts with an M, magnetic field is actually symbol B. Don't know why. So the next thing about magnetic fields is that there's no positive and negative field. There's no positive and negative pole. There's North Pole, there's South Pole. Don't say positive pole. There's no such thing. Santa lives at the North Pole, right? Not the positive pole. All right, the next thing I have us do is look at some variety of metals. So I have a big giant permanent magnet. A permanent magnet is called ferromagnetic. And there are only certain materials that are ferromagnetic. You'll see that more in the YouTube videos. So I have you take this magnet and I have you bring it near aluminum. And it's like, tink, 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 tink. Oh, not exciting. No attraction. But then I have you bring it near, let's say, a paperclip. And it's like, bing. And then maybe I have you bring that whole system near another paperclip. It's like, ding. And then all of a sudden, you have this paperclip chain, ding, hanging off your magnet. What those paperclips do is they're paramagnetic, which means when they're exposed to the magnetic field made by this permanent magnet, they also become magnetic in that same way. Again, you'll find a lot of the metal screws are also pink magnetic, and you can make this continuing magnetic chain with them. So that's pretty exciting. So you have paramagnetic, ferromagnetic. There's also diamagnetic, which is a reaction to the field, but in the kind of 90-degree orientation. So you'll see that a little bit more in the video too. Okay, the next thing I have you do is check out this solenoid with a compass. So a solenoid, you know my spelling is great, is just basically a coil of wire, and you take that wire and you attach it to some sort of battery source, and you pump some current through it. So if you were to trace the current, it would come out of the positive end of the battery up front here, and it would go through these wires. And so I ask you to take a compass and trace around it. And so let's go ahead and stick our compass inside. As you begin to do that, the compass will rotate. And it will align its little magnetic field, its north, with the north created by the solenoid. And as you begin to probe more places in the inside, you see that no matter where you probe, up, down, in the middle, anywhere in the inside has this same directed compass. Now, as you start to bring that compass on the outside, over here, your needle is going to bend a little bit. this. And then over here, sorry, you have a little bit more bending. So like this. Here's another one, and it will bend like this. And so we have this kind of field created by a solenoid that is uniform within the inside. So B blue. So we have a magnetic field that is uniform on the inside. No matter where you put your compass detector, it's always going to point that same way, never towards any of the wires. Then it points out this end, around like this, and back in. So notice that this definition of north is the same direction as the B points. So these guys all point with their north end, and the magnetic field points as well. All right, magnetic field, symbol B. Okay, another thing I have you check out is what happens when you run a current just through a regular single loop of wire. So we take our current, comes out of this wire, goes around like this, right, current I. We'll take our magnet here, and if there's no current, it just lays like this, our compass, I mean. But as soon as we turn that on, we get a magnetic field, and our compass is going to oscillate to align with that magnetic field. Notice that there's this perpendicular nature, right? The I is to the right, and this B is pointed this way on top of the wire. And you can take this compass and curl it around if you want to get more results. Again, here we have this nature where the I, for example, is up right here, and the B is to the left. So again, this kind of perpendicular nature. The next thing I do is I take some wires, and I suspend them from a ring stand. So I just take this loop, and I pump some current through it again, like this. I is coming into this loop, and all around the loop, I. And I have you take a compass, and I have you bring it near this loop. And as our compass comes near the loop, it's going to be really hard for me to draw this one. Let's see. The north end of our compass will change to point in the direction of north that this loop makes. And it's kind of a interesting drawing for me because given that perpendicular nature, right, I is in this XY plane, and so the B ends up actually pointing in. Now, as soon as you flip your battery around, so let's erase this battery here and flip it. So now our battery is going to look like this, small over here and larger over here. And our current will come out in the other way. Oh, other way. Coming up here. And so then it'll go around the loop in the opposite manner as we had before. So instead of going around clockwise, it's going to come around in this way, and it's going to go around counterclockwise. And this time, when we bring our compass close, what happens is the inner needle is going to switch so that instead of the north end pointing kind of into the loop, the north end points out of the loop. So this magnetic field created in this current situation is out of the loop. So it comes down to there's two types of magnets that we create and explore in this session here. We have this idea of permanent magnets. These are the type that attach to your fridge. And then we have all of these other magnets over here, right? All of these ones, these are electromagnets. And it may seem that even though permanent magnets are the ones that you interact with, permanent, whatever, they're the ones you interact with more commonly. Electromagnets are actually more predictable magnetic fields that we can use to predict some interactions. So we will mainly be focusing on electromagnets. All right, so I'm on our first page of our magnetostatics packet. So that just means magnets without moving. Let's look at a bar magnet. So a bar magnet is defined as a permanent magnet and is the most common magnet that you will experience in your daily life. And so every bar magnet has a north and a south end. And if you cut it in half, it'll still have a north and a south end. It's impossible to have a magnetic monopole, meaning just a north or just a south. You'll create two smaller magnets if you break it in half. So let's look at the magnetic field, symbol B. that comes out of this bar magnet. So here we have this magnetic field. It comes out of the north, loops around, and back into the south. Now, the interesting thing about magnetic field lines is even if you can't draw it because the rest of the paper is in the way or that goes around the entire Earth, like this one, they're always closed lines. This is different than the electric field, where the electric field just went out to radially to infinity. So these are closed circles, so that when we enter inside the magnet and continue tracing, we have this from south to north situation. So our magnetic field goes out the north, into the south. And then through the magnet, right, goes south to north, obviously. And they're always closed loops. So the next type of magnet we're going to deal with is an electromagnet. An electromagnet comes because you're sending current in a loop. And from our stations, you would have discovered this, current in a loop. So current in a loop makes a magnetic field where the north end points out north. And again, these all loop around. So only in the very center of the loop does the magnetic field point straight. And all the other ones is a little bit bent, right? All of these are closed loops. Again, out of the north into the south, and then in the magnet goes south to north. So when you are interested in getting the direction of this north, you're going to have to use your right hand to figure out just the basic directions of positives. So let me show you what I mean. So when we are trying to find the magnetic field of this current conducting loop, we're going to take our right hand and just put it flat with a piece of paper. You're going to take your fingers and loop around where I is. So do you see I goes behind and then in front? And then our thumb points to the right. And our thumb shows that direction of north. So our current goes behind and our north end to the right. So now let's say we have a straight piece of wire like this, where our current runs along. We can use the same idea of our right hand, allowing our thumb to now be I and our fingers to be B. And we'll find that the magnetic field is now circling a straight wire, B. Sometimes the symbol for B, as drawing these kind of loops around the wire, can be difficult. Sometimes people say the B goes in at the top and out at the bottom. So these are symbols that mean in and out. You can think about them as perhaps the tip of an arrow, right, entering a piece of paper. So as the tip goes in first, the last thing you'll see is the little tail feathers, which make that kind of X pattern. And then as it's coming out of the page, you'll see the tip of the arrow penetrating through the paper. I just think X marks the spot, and like dig in here for the treasure, for example. And this looks like an eye looking out at you. So that's my technique. Do whatever you like. Let me show you how to set up your right hand to get the direction of B around a current I. Okay, so this time we'll take our right hand and we'll align it with the paper. This time we'll let our thumb be I and our fingers be B. So we'll take our thumb and we'll put it to the left and let our fingers wrap around. See that our fingers go in above our thumb, behind, and out below our thumb, where our thumb represents I, which is in the wire. So again, B is in, behind, and out. And you're just looking at what they're doing, the B field, with I being the wire. This is similar and different to the example done up here, because up here we choose to make our fingers I and our thumb B. So we're doing more of this. It doesn't matter which one is which. It just, if these are I, then this is B. Your fingers are much easier to wrap, so let them be whatever moves in a circle. There's always one thing that's kind of circular and one thing that's straight, due to the nature of B and I. Okay, so here I set up some different currents for you to practice your right hand rule. So you can predict which direction the magnetic field will be around these different currents. So first you have a current in a counterclockwise loop, then a current moving to the right, and then a current that has this X symbol. Pause, try it out. Okay, here we go. So when I use my right hand to represent this I, here's what I get. I take my fingers to be the I, and my fingers are going to wrap around this way, which means my thumb then points out. which allows me to know that my B is out. Okie dokie, let's go on to the next one. In this next one, I have my current to the right. So I'm going to take my hand and I'm going to put it like this, where my thumb is the current, and it is also to the right. My current is to the right, well, generally, I guess. And then my B is coming around and up like this, B. So my current comes around, behind, and up like this, and then in front. So another way to show that is that perhaps my B, my fingers are pointing out here and in here, because making that wraparound is a little bit challenging. Okay, next one. I felt a little awkward doing this one. Here's how you set it up. So in this case, you know that the current is the symbol X, which means in, dig in, for example. Then that leads my fingers to wrap around like this, which show my B. So my B will travel around my I like this. This is great practice using your right hand rule.